This paper explores the development of large neural video coding models, focusing on scaling up model sizes and architectures to enhance video compression performance. It begins by discussing the success of large language models, LLMs, and large vision models, LVMs, in natural language understanding and computer vision tasks, respectively. These models have achieved significant improvements in performance as their model sizes increase, following the scaling law. The paper then reviews neural video coding schemes, which represent a new direction for video compression. Motion compensation-based schemes, such as DVC, MLVC, SSF, FVC, DCVC, DCVC-TCM, DCVC-HEM, DCVC-DC, and DCVC-SDD, have achieved state-of-the-art compression performance. However, these models have small model sizes, and no research has explored the effectiveness of scaling up the model size of neural video coding models. To address this gap, the authors propose a large neural video coding model called NVC-1B, with more than 1 billion parameters. They first analyze the influence of model sizes on compression performance by gradually scaling up the model sizes of different parts of a neural video coding model. They also explore different architectures, including CNN, mixed CNN transformer, and transformer architectures, to implement the neural video coding model and analyze the influence of model architectures on compression performance. The proposed NVC-1B model is based on the small baseline model DCVC-SDD, which has a higher compression performance than the reference software of H266, VVC under certain testing conditions. The author's exploration results show that scaling up the model size and changing the model architecture can significantly improve video compression performance. Consequently, they achieve the state-of-the-art compression efficiency with NVC-1B. This work anticipates that large models may bring video coding technologies to the next level. This paper presents a large neural video coding model, NVC-1B, which is designed to explore the influence of model size on compression performance. The proposed model consists of several key components including motion estimation, motion encoder-decoder, temporal context mining, contextual encoder-decoder, and entropy models. The authors first provide an overview of the NVC-1B framework, detailing the process from motion estimation to contextual encoding and decoding. They then delve into the methodology, focusing on scaling up different parts of the model to analyze their impact on compression performance. The authors explore the influence of model size by gradually increasing the model size of different parts, such as motion encoder-decoder, motion entropy model, contextual encoder-decoder, and contextual entropy model. They observe that scaling up the model size of the motion encoder-decoder and motion entropy model can bring performance gains, but larger models may lead to training instability and reduced performance gains. On the other hand, increasing the model size of the contextual encoder-decoder and contextual entropy model consistently improves compression performance without encountering training issues. The paper also includes experimental results comparing the proposed models with their small baseline model DCVC-SDD. The results indicate that scaling up the model size of the contextual encoder-decoder and contextual entropy model can significantly enhance the compression performance, while scaling up the motion encoder-decoder and motion entropy model may not always result in better performance. The authors provide a detailed analysis of these findings in the following sections of the paper. This study explores the impact of scaling up model size and modifying the architecture of a neural video coding model. The authors first investigate the effect of increasing the model size of various components, including the contextual encoder-decoder, contextual entropy model, and temporal context mining module. The results, presented in figures 3 and 4, show that scaling up these components can lead to significant compression performance improvements. For instance, increasing the model size of the contextual entropy model from 90M to 212M yields an additional 0.8% performance gain for the HEVC Class C dataset. The authors then examine the influence of model architecture, specifically the mixed CNN transformer and transformer architectures. They build 3 models, M19, M20, and M21, which incorporate SWIN transformer layers into the contextual encoder-decoder, contextual entropy model, and temporal context mining module, respectively. The results, presented in Figure 5, indicate that the mixed CNN transformer architecture can bring performance gains over the small baseline model, but the CNN architecture counterparts achieve higher video coding performance gains. However, inserting SWIN transformer layers into the temporal context mining module results in performance loss. The authors also investigate the transformer architecture, building 3 models, M22, M23, and M24, which replace the convolutional layers and residual blocks with SWIN transformer layers. The results, presented in Figure 6, show that the transformer-based contextual encoder-decoder can bring a small performance gain, but the transform-only based contextual entropy model and temporal context mining module lead to model crashes. The study concludes that scaling up the model sizes of the contextual encoder-decoder, contextual entropy model, and temporal context mining module can bring continuous compression performance improvements. However, the CNN architecture outperforms the mixed CNN transformer and transformer architectures. Based on these findings, the authors build a large neural video coding model, NVC-1B, with a CNN architecture, allocating most of the model parameters to the contextual encoder-decoder, contextual entropy model, and temporal context mining module. The model is trained using an elaborate strategy, with 6 training stages classified according to the training loss functions. In this research, the authors present a novel neural video coding model called NVC-1B, which significantly outperforms its small baseline model DCVCSDD and state-of-the-art neural video coding models like DCVCDC and DCVCFM. The NVC-1B model is trained using the Vimeo 90K dataset, and its performance is evaluated on the HEVC, UVG, and MCLJCVRGB video datasets. The model uses a hierarchical fine-tuning strategy, where the loss functions are calculated at different stages of the encoding process. These include LMED, LMERD, LRECD, LRECRD, and LOL, which measure the distortion between the original and reconstructed frames, the bitrate of motion vectors, and the overall rate distortion trade-off. The model also utilizes a periodically varying weight WT to reduce error propagation during the cascaded fine-tuning stage. The experimental setup includes training and testing data preparation, implementation details, and evaluation metrics. For RGB videos, RGB-PSNR is used as the distortion evaluation metric, while for YUV420 videos, the compound YUV-PSNR is used with a weight of 6:1. 1 for YUV components. The bitrate is measured in bits per pixel, BPP, and the compression performance is compared using the bitrate, where negative numbers indicate bitrate saving and positive numbers indicate bitrate increasing. The results show that the NVC-1B model achieves an average 25.1% bitrate reduction over VTM 13.2 across all test datasets, surpassing other neural video coding models and traditional video codecs. When testing YUV420 videos, the large model improves the average compression performance from 8.4% to 20.5%, outperforming ECM, 19.0%. The findings suggest that the NVC-1B model can effectively reduce the bitrate while maintaining high-quality reconstructed frames, making it a promising solution for neural video coding. The proposed large neural video coding model, NVC-1B, is evaluated on various video datasets, including HEVC Class B, C, D, and E, as well as UVG and MCLJCV. The rate distortion curves in Fig. 8 demonstrate that NVC-1B achieves significant performance gains over traditional video codecs, such as HEVC, UVG, and MCLJCV. Specifically, NVC-1B outperforms the state-of-the-art model, ECM, in terms of UV-PSNR. The bitrate comparison in Table IV shows that NVC-1B achieves an average bitrate reduction of 20.5% compared to VTM. The subjective comparison results in Fig. 9 demonstrate that NVC-1B can retain more textures with a lower bitrate than its small baseline model, DCVCSDD. For example, in the video SRC14 sequence, NVC-1B achieves a reconstructed frame of 37.52 decibels at a bitrate of 0.051 bpp, while DCV-CSDD achieves 37.46 decibels at a bitrate of 0.057 bpp. The encoding and decoding times of NVC-1B are 4.44s and 3.54s per frame, respectively, which are 5 times longer than that of DCV-CSDD. However, the encoding time of NVC-1B is significantly lower than that of traditional video codecs. The analysis of transform energy compaction in Fig. 10 shows that NVC-1B can effectively compact the energy of the contextual latent representation. The average contextual bitrate ratio of each channel is calculated using equation 7, and the top 100 channels with obvious energy compaction are presented. The results demonstrate that NVC-1B can efficiently allocate bits to the most important channels, leading to improved compression performance. The performance gain of NVC-1B is mainly attributed to its ability to use more frames for multi-frame cascaded fine-tuning. However, the number of frames used is limited by the GPU CUDA memory. If larger CUDA memory is available, the performance of NVC-1B can be further improved. The encoding and decoding times of NVC-1B can be optimized using lightweight techniques for large models. The paper presents an in-depth analysis of the influence of model size on compression performance in neural video coding. The authors scale up the model sizes of different parts of a neural video coding model and explore the effect on compression performance. They also analyze the influence of model architecture on compression performance by implementing different architectures. The results show that increasing the model size of the motion encoder-decoder can lead to performance gains, but the gain decreases if the model size is continuously increased. The authors also visualize the warp frames predicted by different models and find that an inappropriate model size can reduce the accuracy of temporal prediction. The paper also presents a large neural video coding model, NVC-1B, which achieves a significant video compression gain over its small baseline model. The authors analyze the temporal context mining accuracy and find that NVC-1B can obtain a higher compression performance by improving the temporal context mining accuracy. The motion channel bitrate distribution of NVC-1B is also more concentrated, indicating that more signal energy is concentrated in fewer channels, which is beneficial for entropy coding. The authors further analyze the transform energy compaction of the contextual latent representations generated by NVC-1B and its small baseline model. The results show that NVC-1B has higher transform energy compaction, indicating that more bitrates are concentrated in fewer channels. The paper concludes by highlighting the importance of considering both model size and architecture in neural video coding. The authors suggest that future work should focus on designing larger models with more efficient architectures to further improve video compression performance. In terms of related work, the paper cites various studies on neural video coding, including works on learned video compression, neural interframe compression, and end-to-end optimized video compression. The authors also reference studies on scaling laws for neural language models and the use of transformers for image recognition. The referenced papers and citations on pages 13 and 14 of the research paper provide a comprehensive overview of the current state of neural video coding models, language models, and image compression techniques. The authors draw upon a wide range of sources, including recent conference proceedings, journal articles, and preprints, to establish the foundation for their research. The citations highlight the development of large neural models, such as vision transformers and language models, which have achieved state-of-the-art performance in various tasks. For instance, the SWIN transformer V2 and the Llama model are mentioned as examples of scalable and efficient architectures. The authors also reference the use of mixture of experts and pathways for scaling language models, as seen in the GLAM and PaLM models. In the context of video compression, the authors cite various techniques, including deep video compression frameworks, coarse-to-fine coding, and end-to-end neural video coding. The use of optical flow estimation in spatial pyramid networks is also mentioned as a means of improving video compression. Furthermore, the authors reference the development of image compression techniques, such as variational image compression and transformer-based image compression. The citations also highlight the importance of evaluating the performance of video compression models using standardized test conditions and software reference configurations. The authors reference the use of datasets, such as the UVG dataset and the MCLJCV dataset, for evaluating video codec performance. The authors also draw upon optimization techniques, such as atom optimization, and evaluation metrics, such as PSNR and B-Drate, to assess the performance of their proposed model. The use of low-rank adaptation and generative inference is also mentioned as a means of improving the efficiency of large language models. Overall, the citations on pages 13 and 14 provide a comprehensive overview of the current state of neural video coding models, language models, and image compression techniques, highlighting the key techniques, architectures, and evaluation metrics used in these fields.